So, hello everyone. Today we will study about steady state modeling and performance of grid connected voltage source converter. So, with this steady state model of the voltage source converter, we will know what are the steady state currents, power, etc., which is getting exchanged with the voltage source converter and with the grid. Okay, how is the exchange happening? After this we will study about the dynamic model. Okay. But let us start with the steady state models. So, the content is something like this: steady state modeling, the power flow and how to implement them in simulation. Okay. So, the grid connected voltage source converter. So, we have talked about multi-level converters, different types of multi-level converters, but they can all be classified or categorized under the umbrella of voltage source converter. So, we have studied different multi-level converters like cascaded edge bridge, neutral point clamp, modular multi-level converter, whatever, but these are all these are all classified as voltage source converters. Okay. The easiest example of a voltage source converter is a two level converter, okay, which has one DC link and 6 switches. Now, whatever may be the voltage source converter, when they are connected to the grid, we usually connect them through a filter. Okay. As I have shown you in this diagram, you have the voltage source converter, you have the AC grid, 3-phase grid and the filter. Now, there can be different types of filters, okay, like L filter, LC filter, LCL filter and even higher than that also. Now, in this course, okay, now L filter is the easiest filter. Okay. L filter is basically, which we have represented here, it is basically an inductor. In a 3-phase system, it is a 3-phase inductor, and this RF which we have shown in the diagram, the RF is nothing but the resistance of this inductor. Now, this is the simplest filter. Okay. Now, it has some limited performance. Okay. Although it is simple, but it has some performance limitations. Okay. For example, the harmonics that are that flows from the voltage source converter into the grid is attenuated to a limited fashion with this kind of an L filter. You can have higher order filters like LC or LCL, but in this course, since we are talking mostly about multi-level converters, we will restrict the analysis within L filter only. Okay. Now, in case of a multi-level converter, we see that the voltage waveforms which are produced by this VSC or the voltage source converter, this is already highly sinusoidal. We have seen so far there are many steps in the waveforms and they have become highly sinusoidal, and for that reason a small L filter is often sufficient to interface with the grid. Okay. Because the voltage waveform of the voltage source converter is already quite sinusoidal, so a small L filter is often sufficient. Okay. Now, we will see this in details. Basically, what you can understand here is that the L filter is basically working like this thing. The voltage source converter, from our analysis so far, this voltage source converter is nothing but a controllable voltage source, and this filter, if I assume that the resistance is very small, is nothing but a small L, and the grid is also a AC source. So, basically you can immediately see that this is nothing but two AC sources V1, V2 and an inductance in between. Okay. This is what the circuit is all about. Okay. I should not draw this like this. So, I will draw it like this. Okay. So, this is what is the entire circuit, okay, with the X filter. Now, since V1 is not, so V2 is the grid and it is a sine wave. Okay. V1 is not sine wave, okay. It is a pulsating waveform, PWM pulsating waveform. So, this is not a sine wave, but with multi-level converters, this waveform becomes almost a sine wave. Okay. So, when you have these two sine waves, the power exchange and the current exchange is controlled by the X or the filter in between. Okay. Now, you can have other types of filters also, but for this multi-level converters, a small X which interfaces with the grid is sufficient. Okay. Now, the multi-level converter. So, why do we need the X? First of all, we need the X because we want to control the power flow between V1 and V2. We will want to control the power flow between the voltage source converter and the grid. So, that is why an interfacing inductor is needed, X is needed in between. And there is also one more reason why this X or the L is needed, is because if there is a short circuit here, okay, if there is a short circuit here, then the X or that L filter, the impedance of that L filter X, that actually controls the rate of rise of the current through the VSC. In order to limit that current, okay, we put an X. Okay. So, X has two purposes, the L filter has two purposes. First, it allows us to exchange or control the power flow between the voltage source converter and the grid, that is the first functionality. The second functionality is that the L filter helps us to control the rate of rise of current in the event of a short circuit at the output or at the grid side. Let us see the basic converters, how do we model it and what are the governing equations for the converter. In order to understand the governing equations, we see that we are revisiting one of the slides which we have earlier covered, and in this slide we show the VAN, VBN, VCN as a function of the pole voltages. Okay. So, here you can see the VAN voltage, VBN and VCN voltages. These are the voltages which are appearing between the points A and N here. Okay. So, this is the VAN, VBN, VCN which we have also earlier seen. We have derived this equation, and this VAO is the pole voltage, O point stands here and VAO is the pole voltage. So, VAN is nothing but a combination of the three pole voltages. Now, for how do I know what is VAO? Okay. So, when we implement in simulation, okay, the VAO, VBO and VCO, how do I know? So, it is a very easy way, like you know VAO, VBO, VCO. So, I will have this as like VAN, VBN, VCN, and the input is VAO, VBO and VCO. Okay. And so, if this equation, I give the name equation here. So, this is the equation which is running to get VAN from VAO, VBO, VCO. Now, how do I get VAO, VBO, VCO? In order to get VAO, VBO, VCO, what I will give to this block is the switching signals SA, SB and SC, okay, and I will give the information of VDC and I will get VAO, VBO and VCO, right. So, what are these SA, SB, SC? Say for example, SA can be 0 or 1, okay. That means this switch here, this is these two switches are represented by SA, okay. So, SA can be 0 or 1. So, VAO, the voltage VAO, so if you put a switch here, okay, if you put a switch here, VAO is either 1 or 0, okay, multiplied by the DC bus voltage. Okay. So, this is the DC bus voltage here at the bottom, which corresponds to this VD here. So, this is the DC bus voltage. So, you have a logic here, okay, very simple logic, where you can by getting the values of SA, SB, SC, I can with the help of the VDC I can have the VAO, VBO and VCO. And how do I get SA, SB, SC? I get this SA, SB, SC from the comparison. So, here I will have the triangle which is like this, and I will have the VA star, VB star, VC star. Okay. So, VA star, VB star, VC star. So, here is a comparison. Okay. So, as we have already seen earlier, VA star, if you compare with the triangle, if the modulating wave is more than the triangle, then you get the SA, then you get the turn on the upper switch, otherwise you turn on the lower switch. So, this is how the whole logic is being developed. And where do I get this VA star, VB star, VC star? So, I get this VA star. So, this thing, this I will get, we will talk about this, this we will get from the controller, control system, okay, control system. Control system will give us these three values, okay, which we will put as this VA star, VB star, VC star. We can add the third harmonic also. Anyway, so this is the whole block which you can develop. So, what I said, what I mean here, what implementing in simulation, above equations can be treated as a block. So, for example, if you have this one SA, SB, SC, so this is a block which represents this equation here. Okay. So, this is what it's all about. Now, so this was the implementation of the voltage source converter, internal details of the voltage source converter in simulation. But now, let us do the modeling of the voltage source converter in the steady state. Okay. Now, when you do the modeling at steady state, you have to remember certain important points, and this is what we will discuss now. So, here you can see what I have shown here. Here is the converter, you can see on the left is a converter, and here is a grid, and then there is a filter here. So, the converter is basically a controllable voltage source, right. So, this is the point V A, we are taking only the A phase, and so VAO is this voltage here coming from the converter, and VAN, okay, VAN, this voltage VAN, this voltage here is the voltage between the converter output and the grid neutral point, okay. The grid's neutral point and the converter's output voltage, that voltage is VAN, okay, which we are terming as VAN. This is the voltage that is getting impressed here on that, on the circuit. What is this VAN? This VAN is nothing but this VAN here, okay. This is the VAN, VBN, VCN, and this VAN, VCN, VCN, this is the VAN. Okay. So, this VAN is nothing but 2/3 VAO minus 1/3 VBO minus 1/3 VCO. So, this is the VAN which when we put it into a circuit, which we treat it like this. Okay. We put this one here. Okay. So, what we do here is that we assume, so from this circuit, this is the actual circuit. Okay. On the left is the actual circuit and on the right is the equivalent single phase circuit. So, here on the right hand side you see that the VAN voltage is a controllable voltage which we have said. Okay. This is the controllable voltage. Okay. So, I should actually not write it, this is N. Okay. So, this is the VAN voltage, it is a controllable voltage. Now, this is the converter's controllable voltage and this is the grid voltage VAG, this is the grid here, this is the grid and this is the converter. Now, this is the voltage VAN which is here, this is the voltage, this is the VAN voltage which we have, this voltage is present here on the converter. Now, the point N here and the point N here, note this very carefully, these 2 points are at the same potential. Okay. The point N here and the point N here, N is the converter neutral and the right hand side N is the grid neutral. They are at the same potential. Okay. They are at the same potential, but they are not physically connected, very important here, they are physically disconnected. So, these 2 points actually are physically disconnected because the converter's DC bus is no way connected to the grid. So, in most of the cases if it is a 3 phase 3 wire system, the grid has an isolated neutral, the converter has an isolated neutral. Okay. So, the converter's neutral and the grid's neutral, they are not connected, they are never physically connected. But when we do the modeling, we come to this VAN here, which is again a function of VAO, VBO and VCO. This VAN has this end point here and the converter's end point is at this right hand side, they are at the same potential. Okay. And then we can model it and then we know what is the current flowing. Okay. So, I could have also, so for example, I could have also connected these 2 points, okay, because only if I connect these 2 points I can complete the KVL equation and then I can say how much is the current flowing. Okay. I can write only when I connect it, but I have not connected it. Okay. Although I know that these 2 points are at the same potential, so I will not connect it because they are physically connected, they are physically disconnected, they are not connected. Okay. But if I want to know what is I, okay, I have to assume that they are at the same potential and there is a path for the current to flow. Okay. Only then I can write the KVL equation and can write. Okay. So, this concept must be very clearly understood that the converter. So, when you are in a single phase system, okay, of course, when you do the 3 phase system it will be more clearer to you, but when you have the single phase system, when you want to analyze the single phase model of the 3 phase VSC, then we make the model something like this, what I have shown on the right hand side, where you have the grid voltage on the right, we have the RF and LF, okay, this is the filter, okay, you can have other types of filters also, and then there is a VAN voltage and that is the converter's voltage and that VAN is related to the pole voltages by this equation. Okay. So, VAN is related to the pole voltages by this pole voltage of the converter and this VAN voltage is not same, they are not same, okay, they are different, but this is the VAN voltage when we use in the modeling, okay, VAN, and then this is the grid voltage. Okay. It should be clearly understood. Okay. So, when I now when I extrapolate it and I go to the 3 phase system, now you will fully understand what we mean here. Okay. So, this is the voltage source converter. On the left hand side you have the voltage source converter, you have this A point, B points and C points, and here you can see the grid. So, this is the say this is the VAG, this is the VBG and this is the VCG. Okay. These are the 3 voltages and these are the filters. Okay. So, this is ZF and ZF and ZF here. Okay. So, this voltage VAN, okay, this is the voltage which you see here, this is the point A and here is the point N. Okay. So, this is the VAN voltage. Okay. So, this is the voltage which is present here. And the voltage of N and the G, the VAG, when we say VAG, this is the G here, okay, that is the grid's neutral point. Okay. So, we assume that they are at the same potential. Okay. The 2 neutrals are at the same potential, but they are physically disconnected. Okay. And so, therefore, the 3 phase system can be, the 3 phase VSC can be modeled by this diagram which I have shown you. Okay. VAN, RF, LF and VAG. Okay. And this VAN is like 2/3 VAO minus 1/3 VBO minus 1/3 VCO, and VAO is again a combination of SA times VDC. SA can be 1 or 0. Okay. So, this is how the chain forms. Now, remember that the voltage VAN, this voltage here, this voltage may contain other harmonics. Okay. So, this may not be simple fundamental. So, this is fundamental, the grid voltage is fundamental, this is fundamental, okay. But the voltage VAN, this voltage here can have fundamental plus 3rd harmonic plus 9th harmonic plus 15th harmonic, something like that. Suppose you add only the 3rd harmonic, then it is the something which we have studied earlier, that you can add triplet harmonics to maximize the DC bus. But if you use like space vector PWM, you are basically adding all triplet harmonics, 3rd, 9th, 15th, etc. But where are you adding? You are basically adding into the VAN voltage. Okay. So, this voltage VAN is maybe a single fundamental voltage source. If you use sine PWM, it is just a fundamental voltage source. So, the equation which I have shown here. So, if this is fundamental, so let me write it. So, if this is fundamental, then we are using sine PWM and the circuit is exactly like this. Okay. However, I will draw it with a different color. If I add, I can add certain harmonics here. Okay. These harmonics can be 3rd, can be 9th or something like that, different types of triplet harmonics. Then we go into something like SBPWM. Now, one of the characteristics of this voltage source, so I will say this is VH or harmonic voltage source. This is a common mode voltage. Okay. very important to understand that this is a common mode voltage, which means this same harmonics we are adding to all the 3 phases at the same time. So, this green colored voltages, this is the common mode. Okay. So, this is the common mode voltage. So, this common mode voltage, what it does is, since this is a common mode voltage, if you see the circuit, it will not be able to inject any current, because it is a common mode, it is same for all the 3 phases. So, there cannot be any current. Okay. So, this is not possible. So, this current cannot flow. So, there will be existing a common mode voltage in all the 3 phases, but there cannot be any current flowing. IgA, IgB and IgC cannot have this harmonic, the 3rd harmonic or 9th harmonic or 5th harmonic and 15th harmonic. Those current cannot flow, because why it cannot flow? Because this neutral here and this neutral here, they are completely isolated. Okay. So, now you understand why these 2 neutrals are completely isolated, okay, because the 3rd harmonics etc. So, we are creating this harmonic voltage, we are deliberately injecting that harmonic voltage, but there is no current flowing. If I had connected this point to this point, that is a 3 phase 4 wire system, then the harmonics will start to flow, then the 3rd harmonic will start to flow, okay, then it will get a path. Otherwise, most of the cases this is not there, 3 phase 3 wire system, it is not there. So, the harmonic voltages will appear, okay, but it cannot inject a current into the system. Then why did we add this VH? Because we added the VH in such a way that we get more VAN. As I told you earlier, that if this is Vn, we add the 3rd harmonic in such a way that we push the VAN voltage something like this. Okay. So, we get 15% more by doing that, we get 15% more of the fundamental. So, here this gets increased by 15%, this gets increased by 15% by adding the common mode voltage, that VH. Okay. But the benefit is that the VH cannot cause the current to flow. So, no harmonic. So, if it is harmonics will not be able to flow in this IgA, IgB and IgC, but the voltage will exist. Okay. In fact, if you see the line voltages, for example, you see this line voltage here, okay, this line voltage V line, you will not see the harmonic voltage, you will not see the 3rd harmonic, you will not see the triplet. Okay. In the line voltage it will not exist. Okay. So, so this is important for us to understand, and you can have different types of common mode voltage. It is not necessary that you have a 3rd or 9th, you can have different types of common mode voltages. Okay. But the benefit of this common mode voltage is that we try to get more fundamental VAN, VBN and VCN, as we had earlier discussed in one of the previous lectures.